Today, our topic is related to energy resources and transfer, and subtopic is related to conservation of energy. And if I talk about energy, energy is basically ability of body to do work. Ability of body to do work is called energy over there. Energy is a scalar quantity measured in joules over there. Joules over there. And if I talk about energy in detail, then I will say here that energy transfers from source to sink over there. Means the phenomenon which I am want to tell you here, source to sink. For example, if we talk about uh, the plants which are producing food by the process of photosynthesis, they are transferring from leaves to all other parts of body of the plant over there. Or where the energy is deficient is being transferred over there. So energy can be held in different stores over there, like energy is transferred between energy stores. Energy is transferred between energy sources over there, energy stores over there. So I can say here uh, about like how uh, these stores you need to learn, plus the examples of objects with energy in each these stores over there. For example, first of all, I am saying kinetic energy. The first one, kinetic energy. This is the energy which is stored in any body due to motion of any object over there. So that is called anything moving has energy in its kinetic energy store over there. After that, thermal energy. This is the energy store which is kept by a body due to difference of temperature over there, and energy is transferred due to temperature difference. After that, chemical energy, in which is released in the form of chemical reactions. Chemical energy over there. This is the type of energy which is carried by anything that can release energy by a chemical reaction, like food and fuels over there. Food and fuels over there, we will have to take into account for energy transfer in the molecules of chemical reactions over there. After that, if I will talk about gravitational potential energy, the energy carried by a plant, carried by an object due to some height, gravitational potential energy over there. The energy stored in a body due to position or due to height over there will be named as anything in gravitational field strength, anything which can fall over there having gravitational potential energy. And after that, there is elastic potential energy. In any elastic body, due to compress or extension, energy is stored, and that energy store is called elastic potential energy of that object over there. After that, magnetic and nuclear energies are also available, which we can say magnets will have the energy that will be stored in the form of attraction or repulsion. And there is nuclear energy also available over there, which is being responsible for atomic nuclei release in the store in the nuclear reactions, which we mostly take as nuclear fusion and nuclear fusion and nuclear fission over there. Fusion is when smaller nuclei are going to mix up to make a bigger one, and fission is when bigger one is going to be broken down into two or more smaller nuclei, happening in an atom bomb or like that, or should be taken over there. After that, energy can be transferred between stores in four main ways over there. These were the energy stores. Then I will say how energy is transferred between the stores. That is having the four main principles. That is mechanically, it is transferred. If I say how mechanically energy is transferred, an object moving due to force acting on it, pushing, pulling, stretching, or squashing, then mechanically an object will be moving and energy will be transferred over there. Moving due to force acting on it. After that, number two is for transferred between stores of energy is done because of electrically behavior. If I talk about electrically, then I will say a charge moving through a potential difference, charge moving around a circuit, then electrically energy is transferred. At number three, I will say by heating. The energy which is transferred due to difference of temperature from hotter body to colder body in the form of convection, conduction, or radiation like that. So we will take due to difference of temperature by heating purpose and by radiation over there. Radiations over there. Like we can say energy is transferred by light, sound waves, energy from the sun reaching to the earth as light. Everything is talking about radiations for transfer of energy. There is a principle of conservation of energy. Principle of conservation of energy, in which I will say energy can neither be created, can neither be created nor be destroyed over there. Be created nor be destroyed. It only changes from one form to another. So according to this law, we can say that energy can be stored, transferred between stores, and dissipated, but it can never be created nor be destroyed. Total energy of closed system has no net change over there. A closed system is just a system or a collection of objects that can be treated completely on its own without any matter being exchanged with the surrounding over there. So it is taken for isolated system, should be taken into account to explain this whole behavior of law of conservation of energy over there. Post energy transfers involve some losses, often by heating. Like we can say energy is only useful when it is transferred from one store to a useful store over there. Means some energy will be lost during that useful stores over there. And for that one, I will simply say here that how efficiency is going on and how we will take to it into account over there. Then I will say here that, for example, I am taking a useful device. I will say here I am taking here a useful device. I am giving it an input energy. This is my useful input energy. I am getting output energy by this device, and some energy wasted is also present over there. then we can say some energy is lost into surrounding by in the form of heat, in the form of noise, or like that. For that purpose, I will say here total energy is equal to energy input is equal to output, useful output energy plus energy wasted, yeah, energy lost. So this is the way how to go for total energy for its calculation over there. So law of conservation of energy also going to be considering that the less energy that is wasted, the more efficient will be the device. So if I talk about the efficiency of the device, which is getting some input energy to give me output energy with less energy wasted, then I will say my this useful device is much more efficient over there. And remember that it is impossible to devise an instrument with 100% efficiency over there. So energy will always be lost when you are talking to transfer it from one form to another using some useful device over there. But for that purpose, I will use here a formula of efficiency of a device over there. Then I will say here that efficiency is equal to efficiency is equal to useful output energy, useful output energy over total energy input, total energy input, total energy input multiply by 100, then I will get percentage efficiency of that useful device over there. You should give efficiency as a percentage, like 75%, like that. All devices have an efficiency, but because some energy is always wasted, the efficiency can never equal to 100%, or it should never equal to probability of 1 over there. Probability of always should be less than 1 over there. Efficiency should always less than 100% because it is impossible to devise an instrument with 100% efficiency over there. How to use the formula? Then you will have to find much energy supplied to a machine and total energy input. This equals to the total energy output over there. Our total energy input should be taken, and then getting the output energy and then multiplying by 100. Remember that useful output energy means smaller value should be above, larger value should be small down, and 100 should be getting multiplied to get the percentage efficiency over there. Small value and large value of energy should be used for calculating the efficiency. The other way, they might ask to tell you efficiency and total energy output, then ask for the useful energy output, and they are called to tell you the efficiency and useful output energy, and then you can calculate the total input energy over there. You need to be able to swap the formula around by using the simple algebra over there. So we generally can't do anything with the useful with the wasted energy. The wasted energy that is output by a device is transferred to less useful stores manually, like heating, where the wasted energy is being lost. We can't use it now, or light or sound. Then this wasted energy is not be able to used in an effective way over there. So that is lost over there. As the energy is transferred away from the device to its surrounding, energy often spreads and becomes less concentrated. So we say it is dissipated in these three forms over there. Dissipated in these three forms over there. And according to principle of conservation of energy, the total amount of energy stays the same. So energy is still same, but it cannot easily used or collected back again. Okay. So this will be the way how energy is using the phenomenon of conservation of energy over there. Now I will have to move towards, I will say here, I'm moving towards energy transfers over there. So, more, tell me more about energy than transfers. Okay, sure, we will go with the insisting over there. You need to be able to describe energy transfers over there. In the exam, they can ask you about any device and energy system they feel like. And so it is energy transfers. I am moving towards energy transfers now. How energy is transferred in G transfers. If I talk about it, I will simply say here that, for example, a rolling ball from a slope, how it is going to talk about this. This is a rolling ball from a slope coming downward. What is basically happening? Then basically I can say it is having uh, some potential energy which is stored into this ball over there. Then this potential energy is going to be converted into kinetic energy and also being converted into some thermal energy or sound energy over there. So this is the way how energy is transferred. So energy is transferred mechanically from kinetic energy to which was stored in the form of potential energy over there. And the sum of energy is transferred mechanically to thermal energy and slope due to friction over there. And then heating the thermal energy stores into the surrounding. That energy will be waste energy over there. So remember that when it was at the full peak, it was having gravitational potential energy, and at the full down, it is having the maximum kinetic energy, but it is being lost little bit with the form of heat to the surrounding over there. After that, I am saying a bat hitting a ball. For example, there is a ball which is being hit by a bat over there. Then what is happening over there basically? Some energy is useful transferred mechanically from kinetic energy store of the bat to the kinetic energy store of the ball over there. But when I am saying that kinetic energy from the bat is going towards kinetic energy to the ball while hitting it, then the rest of energy is wasted. Some energy in the kinetic energy stored in the bat is transferred mechanically due to thermal energy stored of the bat and its surrounding, and there was also sound. There was a little bit heat over there, which is a wasted energy in the form of a ball hitting a hard ball over there. After that, I am saying an electric kettle boiling water over there. Electric kettle. If I talk about it, basically I will say here, electric kettle is getting its energy in the form of electricity. So energy is usefully transferred electrically from it, the mains to the thermal energy stored of the kettle for heating element over there. Then I will say electrical energy is transferred to thermal energy for heating purposes of heating filament present in electric kettle. It is then transferred by heating to the thermal energy stored of water over there. Some energy is wasted and transferred by heating from the thermal energy stores of heating element and the water to the thermal energy stores to its surroundings. Thermal energy is little bit lost to surroundings over there. So this is the way how to go for a little bit examples. After that, if I say a powered battery powered toy car like that, then we can say energy is being stored like I'm taking here the example toy car, electrically supported. Then I will say first it is having the electrical energy stored by the battery or powered by the battery over there. Then I will say from chemical energy stores of the battery to the kinetic energy store of the car. It is, first of all, chemical energy is transferred to electrical energy into kinetic energy of the toy car over there, and carried away by light from the headlights, and wasteful energy transferred also occur due to thermal energy stores of the car and surrounding, and wasteful energy is also gone over there. So a little bit light to the also given to the headlights of the toy car over there, and some energy as wasted in the form of sound, in the form of heat to the surroundings over there. If I give one more example, that is Bunsen burner and a beaker. For example, you are providing a Bunsen burner with the beaker over there. What is basically happening that energy is usefully transferred by heating from chemical energy store of the gas, like which is given. For example, I'm taking a beaker over here, which is lying on the surface of a table over there, and I am providing some Bunsen burner heat over there. Then I will say some liquid is present into this beaker. What is basically happening? Energy is transferred from the heating over there to this boiling liquid or heating liquid over there, from the chemical storage of this gas over there. Chemical energy that is being consumed from the gas particles of burning over there, and energy is also wastefully transferred by heating to the thermal energy stores of the stand and surroundings over there. Stands and their surroundings, some heat is lost. So always, if there is an example of energy transfer, then energy transfer happens with some lost energy, shows efficiency of the system. That will be energy transfer with respect to different examples over there. And we will also take these examples that are called energy transfers over there. Always remember that there are Sankey diagrams are also available. Sankey diagrams. What are they? These are party-free diagrams over there, just to explain how the energy is going out and coming in over there. The idea of Sankey diagrams is to make easy to see the glance how much of input energy is being useful and employed towards in the form of how much being wasted. The thicker the arrow, the more energy is represented over there. For example, here I am saying a TV is getting an example. For example, I am saying here some energy is provided to the TV. This is its input energy. By this one, I say some energy is lost in the form of thermal energy over there. And then I am saying here energy usefully transferred in the form of light, that should be narrow one. And energy usefully transferred by sound is much, should be larger. Like this. So here I am saying input energy in the form of electricity is provided. Then this is sound energy. This is light energy. And the last one is wasteful thermal energy. Waste thermal energy. The thickness of arrowhead is telling me the amount of energy consumed in the different patterns of Sankey diagram over there. So always try to take in Sankey diagrams the total values of the graph, how much magnitude they can hold. You can also go with the surface area to consume by that. So overall, for example, let's suppose I say it is given in the form of input energy in the form of 100 joule over there. Then I say the useful energy which is given in the form of sound is 130 joules. For the light, I say it is 20 joules. And for the last one, I say it is 50 joules. Then 50 joules, according to thickness, is going to be shown in the larger value over there as a waste energy. So this is called a Sankey diagram being made for any device. And the thickness of the arrow represents the amount of energy that can be useful, that can be input, that can be waste energy over there, which should be taken over there. After that, I am talking about energy transferred by heating, energy transferred by thermal way over there. Then I will say here, when energy is moving away due to thermal ways, then what will happen and how it is going to talk about. Then thermal conduction of heat over there. Then I am saying here, wait a second, I'm changing the color of my pen over there. Okay, now I am talking about energy transferred by heating over there. Energy transfer by heating. So heating is basically in the form of heat energy. We can say heat. First, I will talk about heat, in which I will say amount of energy transferred, amount of energy transferred from one body to another, from one body to another due to difference of temperature. That is called heat. Measured in, again, we can say joules over there. And energy is transferred by heating through main three methods over there. That is called conduction. That is called convection. That is called radiation. If I talk about thermal radiation, is the transfer of energy by heating by infrared electromagnetic waves over there. These are IR, infrared electromagnetic waves over there. And conduction and convection are energy transfers that involves the transfer of energy by particles over there. Over there. So conduction is the main form of energy of transfer by heating in solids over there. Mostly in the form of metals due to vibratory motion, energy is transferred over there. And convection is the mainly form of heating liquids and gases over there. I think so your concepts are going to be building up. So try to be connected properly with the video over there. Liquids and gases. By heating of them, convection is going to be taken into account. Emission of thermal radiation occurs in solid, liquids, and gases. An object can both absorb and emit these radiations in the form of electromagnetic radiations, IR, infrared radiations, whether or not the conduction or convection also taking place. So for any cooling down, means a cup of tea is getting cooling down, then we can say it is emitting emitting radiations out, or you are putting ice at your table, then what is happening? It is absorbing the heat to make properly melting phenomenon over there. Then we can say it is absorbing the radiations over there, which are present in the form of surroundings, high temperature, because ice is having the lower temperature than its amount at that present value over there. So heat will be absorbed by the ice over there. So bigger the temperature difference, then the faster the energy is transferred between the thermal energy stores of the body to its surrounding, and that makes sense over there. Then we can say if the temperature difference between hot and cold body, then rate of transfer of heat will be faster. Then the rate of transfer of heat, transfer of energy in the form of heat will be faster over there. So if I give you here a little bit example, then I can say from hot to cold energy transfers over there. So thermal radiations involves emission of electromagnetic waves over there. Then thermal radiation can also be called IR radiation over there and consist of purely electromagnetic waves of certain range of frequencies. It is next to visible light and electromagnetic spectrum, which we will have studied in our waves chapter of electromagnetic waves in detail over there. If you want to get the more information according to electromagnetic spectrum, then you can visit to the previous video of the waves of electromagnetic waves over there. And if I talk about you can feel that the radiation, if you stand near some hot like fire, it means you are feeling the hot air coming towards you, and some colors and surfaces absorbs and emit radiation better than other surfaces. We can say that can be a rough surface and that can be shiny surface over there or dull surface over there. Then on the other side, I say smooth or shiny surfaces present over there. Then this will a good reflector, a good, we can say, on the other end, rough and dull is a good absorber for the surface over there. First of all, as I said, conduction happens in solids over there. Conduction is going to happen in solids. Like, for example, you are heating some object at that point, and what is saying energy is being transferring, and this is hot corner of the solid body, and this is the cold corner of a body, and due to vibratory motion in solids, energy is being transferred over there. In solid, the particles are held tightly together, and so when the particle vibrates, it collides with each other to nearby, and the vibrations quickly passes from the particles to particle and heat is transferred. So conduction is a process in which I can say here the process where energy is transferred, where we can say vibrating particles transfer energy, vibrating particles transfer energy, where the vibrating particles transfer energy from their kinetic energy stored from their kinetic energy store. The process where vibrating particles transfer energy from their kinetic energy store to the kinetic energy store of neighboring particles. To the kinetic energy store of vibrating particles or neighboring particles over there. Neighboring particles. So this is the way how conduction is going to be taken into account while considering the conduction process. This process continues throughout the solid, and gradually some of the energy is passed all the way through the solid causing rise in temperature in the other side of the solid over there from the cold side over there. It is going to be responsible for increase of temperature over there and the other side of the solid, and it is then usually transferred to the thermal energy stores of the surrounding. Also, some energy is lost also there to the surrounding over there. You can do the experiment to demonstrate the conduction over there. For example, I am saying here, for example, you are taking a clamp stand over there. This is a clamp stand over which you are saying that you are provided some metal bar over there. This is a metal bar which you have hanged over this. Then what is happening that you are observing your Bunsen burner flame over here to heat it up. And what is happening like you are providing some small beads over its surface. What you will observe here made up of wax over there. Then what will happen? Like this is a metal bar overall. When you are providing uh, heat at this point, then what will happen? That the heat is being start to transfer towards these beads and wax starts melting, which shows that the temperature of the metal rod of this side, which is not directly heated, is going to increase the temperature by the process of conduction, and your beads of wax are going to be melted over there. After that, there is a process of convection over there. In convection, I told, and it is happening mostly with the metals over there. Now I'm moving towards convection, where I said it is happening in liquids and gases over there. That, for example, you are saying here convection occurs um, in only liquids and gases. Then convection occurs when more energetic particles move from hotter region to colder region. For example, here you are taking a beaker of water over there, and you are providing a flame with the help of Bunsen burner. Flame with the help of Bunsen burner over there. Then what is happening? It is getting heat up. Then this is a hotter region, particle starts to move up, and colder particles are starts to move down part of the liquid. So this is the wave in which we can say the particles of liquid or the particle of gas move. The particles of liquid or gas, particles of liquid or gas move from hotter region to colder region is called convection. Is called convection over there. And in this way, they transfer also energy over there. And we can say this is happening with solid or gas or liquid particles over there. And the immersion of a heater is a good example. The immersion heater example is very good over there. Like, for example, if you are provided with, we can say, the same phenomenon which I used here on the beaker will also be happening with the immersion heater over there. That this is immersion heater, which is provided in the dome-shaped object, and your heating element is present in the base over there. What is happening? This base element is providing high heat energy due to its external source. Hot coils like heater coils are present over there. Then the water present, hot water is coming up, and cold water and more denser water is coming downward over there. Cold water is coming down over there. Then I can say that there is a continuous motion of particles over there. And convection currents are all about change in density. Remember that, please. And also remember that convection is most efficient in roundish or squarish countries over there because they allow the convection currents to work best. And shallow, wide containers or tall, thin ones just don't work quite so well. Also note that because of hot water rises up over there, then I can say here because of low density. Because why it is taking hot up? Because of low density over there. And on the other end, you only get convection currents in the water above the heater. The water below it stays cold because there is almost no conduction over there. Below the heater, water stays cold over there. So not to worry about conduction and convection. We will simply say here that they should be taken into account over there. So I will say here, always try to be focused towards your main topic over here. Let's move towards, you can see the convection currents using the colored crystals over there when you are going to heat a potassium permanganate crystal, which is a colorful solution in the beaker, can also be observed in the form of convection currents over there. So energy transfers is a great overall, and you can reduce the rate of energy transfer. How to reduce the rate of energy transfer? How to reduce that? First of all, I will talk about all objects have thermal conductivity. It describes how well an object transfers energy by conduction. Materials with high thermal conductivity transfer energy between their particles quickly. Like if I say, if you don't want to transfer energy at faster rate, you use insulator. If you want to move, then use conductors or metals are used as good conductors. And insulators, like you don't want to transfer the heat at faster rate, then use an insulator material over there. So to reduce the energy transferred away from a system by conduction, materials with low thermal conductivity, this is having low or no thermal conductivity. So I can reduce the rate of transfer of energy over there. So to reduce the convection, you need to stop the fluid moving and prevent the convection current from forming over there. So remove the flow of material. Remove the flow of material for stopping the energy transfer in convection over there. Insulation uses both of these techniques to reduce energy transfers. So insulation uses basically this method. Insulation uses both of these methods of conductors and insulators and convections over there. Insulation such as clothes, blankets, foam, everything is going to do like that. Some colors and surface areas will absorb IR radiations better than others. So IR radiations absorption and emission with the help of shiny and dull surfaces over there. IR radiations should also be taken into account for reducing the rate of energy transfer over there. And so to reduce the energy transfer away from the object by thermal radiations, the object should be designed with the surface of the poor emitter, shiny and white over there, can be taken into account for the proper working of the energy transfer over there. So overall, I have tried to explain you with the conduction, convection, and radiation over there as the heat energy transfer methods over there. And this is our today class. Tomorrow we will move towards work, energy, and power over there. Thank you so much for today. And kindly subscribe my channel and try to be focused with your main lessons so that you can finish your task in a good way.